Welcome to this masterclass on uniform circular motion. We will analyze the physics of objects moving in circular paths at constant speeds. Our session will focus on rigorous mathematical derivations for angular velocity and centripetal acceleration, ensuring you understand both the how and the why of circular dynamics. This flowchart outlines our logical progression. We start by defining angular displacement and velocity, then derive the linear-angular relationship. The core is the rigorous geometric proof for centripetal acceleration, followed by Newton's laws applied to circular paths. In uniform circular motion, an object travels in a circle at a steady speed. However, because the direction of travel is changing, the velocity vector is constantly changing. This is crucial. Even at constant speed, a circular path requires constant acceleration. To measure rotation, we use angular displacement, theta. It is defined as the arc length s divided by the radius r. This unit is the radian. Radians are a natural unit for physics because they directly link linear distance on the circle to the angle turned. Angular velocity, symbolized by omega, tells us how fast the object is rotating. It is the derivative of the angle with respect to time, measured in radians per second. Its direction is determined by the right-hand rule, perpendicular to the plane of rotation. The time for one full lap is the period, capital T. The number of laps per second is the frequency, f. They are mathematical inverses. If a motor spins 10 times per second, its frequency is 10 Hz, and its period is 0.1 seconds. In one full circle, the angle turned is 2 pi radians. Since this takes time t, the angular velocity omega equals 2 pi divided by the period t, or 2 pi times the frequency f. Linear speed is how fast a point on the edge of the circle is moving. In one full lap, the distance is the circumference, 2 pi r. Dividing this by the time period t gives us the tangential speed. Let's link linear and angular speeds. Arc length s equals radius r times theta. Taking the time derivative of both sides shows the rate of change of arc length is linear velocity v, and the rate of change of the angle is omega. The result is versus equals r times omega. This means linear speed increases linearly with the distance from the center for a given rotation rate. Now we enter the heart of circular dynamics, the derivation of centripetal acceleration. We will prove mathematically why an object moving at a constant speed in a circle is always accelerating toward the center. Look at the velocity vectors at 2 points. Although their lengths are identical, their directions are different. The change in velocity is the difference between these two arrows, and this change points toward the center of the circle. To find acceleration, we need the change in velocity, delta versus. We subtract the first velocity vector from the second. Because the speed is constant, the magnitude of both vectors is just versus. We now use geometry to solve for the magnitude of the difference. We compare two similar triangles, one formed by the radii in the displacement and one formed by the velocity vectors. Because velocity is always perpendicular to the radius, these two triangles are geometrically similar, allowing us to set up a ratio. The ratio of the change in velocity to the velocity equals the ratio of the displacement to the radius. By rearranging, the magnitude of the velocity change is the linear speed versus divided by the radius r, multiplied by the displacement. To turn our equation into acceleration, we divide both sides by the time interval delta t. On the left, we have the rate of change of velocity. On the right, we have the rate of change of position. As we shrink the time interval towards 0, the change in velocity per unit time becomes instantaneous acceleration, and the displacement divided by time becomes the instantaneous linear velocity versus. This leads to the final multiplication. The core derivation is complete. Centripetal acceleration equals versus squared divided by r. As you increase speed or decrease the radius of the turn, the required acceleration grows significantly. We can also express centripetal acceleration using angular velocity. By substituting r omega for v, we find that acceleration equals radius times omega squared. This form is often used for spinning rotors. At any point, the velocity vector is tangent to the path, while the acceleration vector is always perpendicular to velocity, pointing directly toward the center. This center-seeking nature is why we call it centripetal. With kinematics defined, we move to dynamics. We will calculate the force required to generate this acceleration and discuss why circular motion is a unique case in work energy theory. Newton's second law applies here. Force equals mass times acceleration. By substituting the v² over r formula, we get the centripetal force, the net force required to pull an object into a curve. Centripetal force does 0 work. Because the force points to the center and the movement is along the edge, the two vectors are at 90 degrees. Since the cosine of 90 is 0, the work done is always 0. Since the force does 0 work, it cannot change the object's kinetic energy. Because kinetic energy is constant, the speed must also remain constant. The force only serves to change direction, not speed. Centripetal force is not a new force. It is a role played by other forces. For the moon, gravity provides the force. For a car turning, friction provides the centripetal force. If the speed is not constant, we have non-uniform circular motion. Two accelerations exist at right angles. The centripetal part changes direction, and the tangential part changes speed. We can combine all our parameters. By substituting the period formula into the acceleration formula, we find that acceleration is proportional to the radius and inversely proportional to the square of the period. Let's double-check our math with dimensions. Speed squared divided by radius results in length per time squared, which is the exact dimension of acceleration, proving our derivation is sound. This table is your quick reference for circular motion. It shows the fundamental angular quantities, their formulas in terms of linear variables, and their standard SI units. Mastering this is key to solving complex orbital problems. There is a beautiful symmetry in physics. For every linear variable, there is an angular equivalent. Position maps to angle, velocity to rotation rate, and acceleration to angular acceleration. A real-world application is the banking of roads. The slanted road allows a component of the normal force to point toward the center, acting as a centripetal force. This lets cars take turns faster without sliding out. Satellites are a famous case of UCM. The gravitational pull of the Earth provides the centripetal force. By setting the gravity formula equal to our centripetal force formula, we can find the exact orbital velocity. When you swing a stone on a string, the tension in the rope provides the inward centripetal force. If the rope breaks, the force vanishes, and the stone flies off in a straight line tangent to the circle. In vector notation, acceleration is negative omega squared times the radius vector. The negative sign is mathematically significant. It means the acceleration vector points back toward the center of rotation. Always be careful with your units. Frequency is measured in hertz, while angular velocity is in radians per second. To convert frequency to omega, you must multiply by 2 pi. While we treat the object as a point mass, in rotation, the distribution of mass relative to the axis also matters. Moving mass further from the center makes it harder to rotate, leading to the concept of moment of inertia. Students often ask about centrifugal force. In a fixed reference frame, it does not exist. The feeling of being pushed outward is inertia, your body trying to keep going straight while the car pulls you into a curve. One last check on the force equation. Mass times acceleration is the dimension of force. Our centripetal formula reduces to mass times length per time squared, the Newton. This confirms our dynamical derivation is correct. To conclude, we have mastered uniform circular motion. We derived the link between linear and rotational speeds, proved the formula for centripetal acceleration, and established that a net inward force is mandatory for any curved path. You now have the mathematical keys to orbit and rotation.